Okay, well, we have another North Central Climate Collaborative webinar for you today. And my name is Hans Schmitz. I am your web host for today. Certainly not a speaker, so I'm going to try to keep that to a minimum. Did want to let you know that this meeting is being recorded. It will be posted to the North Central Climate Collaborative website within about a week. And there will be a couple of polls that we will administer, one as soon as I hand things over, and one at the conclusion of the presentation today. Encourage you to participate in those as your medium by which you're accessing this may allow. And with that, I think we're ready to begin. I turn things over first to Robin Wilson with The Ohio State University, and we'll allow her to give a little further introduction.
Right. Well, thank you everyone for joining us today. So we have kind of a team presentation today, myself and Dr. Erin Wilson, who are going to tag team a bit over the course of the next 40 minutes or so. Hopefully we'll have plenty of time for questions, so be thinking about those things you want to pick our brains about. And we're going to be talking about a project that was funded by the National Institutes of Food and Ag through a program kind of focused on agroecosystem resilience. And we were funded to develop basically a regional integrated model of the Eastern Corn Belt that would look at how farmers are adapting to changing climate conditions and how those adaptations are going to ultimately influence a range of ecosystem services, from food production being obviously a primary one in this region, but also other services such as the provision of clean water, sequestering carbon, and then also looking at that from an economic lens to think about how we could then intervene with different policies or programs that might increase the resilience of the agricultural system in the face of these changes. So that's the kind of big picture overview of where we're going. And I will, over the course of the next 40 minutes, kind of hit just very briefly on all the aspects of the project, but we're going to spend a little more time talking so far about two of our main objectives and the results that we found, which was the climate modeling piece, and then also the farmer decision-making piece in response to the changing climate. So we'll spend a little extra time on that today, as those are the most kind of far along in the process. But we are representing a much bigger team from Ohio State, including some folks from our Department of Agricultural, Environmental, and Development Economics, Erin, who's with Bird Polar and Climate Research Center, Department of Extension, and also Department of Geography. So just a little kind of background and rationale. Some of you might already know this, but climate change in this region is projected to bring higher temperatures, more variable and extreme levels of precipitation, and longer growing seasons. This will induce adaptations. We know that farmers are constantly, at least incrementally, adapting to these sorts of challenges, but we know that some of these challenges will get bigger as we continue into the future. And these changes, the way they choose to adapt to these fluctuations in rainfall and temperature in particular, will depend on both the values and goals of that individual farmer, but also the conditions that are imposed by society at large. So the sorts of policies and programs that might be in place, changes in market structures, right? This is a very dynamic system with lots of moving parts. And so in this project, we're trying to tease that out a bit. And adaptations at both the individual and the societal level will generate trade-offs, but we don't really know what these are. So as a farmer, perhaps in the short term, maybe adds more, increases their drainage system in order to deal with inundations of water in the spring so they can get in there and plant, that could have, negative impacts downstream in terms of water quality. And so we want to start to figure out, like, what are those trade-offs and how can we minimize any of those sort of negative outcomes that might occur. So our research questions are really threefold. How are farmers likely to adapt to these climate-induced risks and uncertainties? How will these changes in land use and management influence the sustainability and resilience of the agroecosystem? And what policies and programs will best balance agricultural production with the protection of critical ecosystem services? So again, more broadly outside of the production of food, feed, and fuel. And so this is our study area. So when we talk about the Eastern Corn Belt, we're thinking about these 5 states. However, we are kind of focusing on the lower parts of Wisconsin and Michigan. Oops, little slide flip there. And what you see here is that while our big kind of economic model will be modeling the region, where we are doing some of our ecosystem services work and where we're collecting data on farmer decision making is limited to these particular watersheds that you see highlighted across the map. So these are our kind of representative watersheds within each of these states that have at least 40% of the land and crops and are similar in a lot of ways. We try to control for some of the variation you might find otherwise across the states, so we could really dig into the farmer decision-making piece and the impact of those decisions on the suite of ecosystem services. And so our first kind of objective in this project, and we'd like to point this out, is we do intensively engage stakeholders through a participatory sort of modeling framework. We're using these processes to improve the usefulness of our models and legitimacy of any analysis we end up doing at the end of the project in terms of policy. So we have a pretty diverse group of stakeholders across the agricultural and environmental spectrum helping us think through these things. We meet with them 4 times a year. They help us solve problems, they ground truth, and they kind of keep us on the straight and narrow. And so we're working with them, everything from kind of getting input on a survey instrument we designed for farmers to helping us design scenarios and do the policy analysis. And the hope is that at the end of the day, this integrated modeling framework will be more accurate. It'll be more familiar to people who might actually be able to use it. And ultimately, any recommendations that might come out of our policy analysis would be more likely to be applied by engaging some of these critical voices throughout the process. The second big objective of the project, and this is where you'll get to hear a little more detail, is developing the future climate projections. So our goal here was to understand the impact of climate variability on ag systems across the Eastern Corn Belt region. Our approach was to assess and analyze high-resolution climate data, specifically projections of future precipitation and temperature variability for the region, and critically evaluate the particular stresses that might impact ag systems, such as planting date shifting or harvest date shifting. And then the outcome is a clearly defined set of scenarios of future climate variability scaled down to the Eastern Corn Belt region. So at this point, I will hand it off to Aaron Wilson, who's been leading that component of the project, and he'll provide you with a little more background on what he's been finding so far.
All right, great. Thank you so much, Robin. And it's fantastic to be here, just echoing your comments today. Fantastic to be here and share what we have to offer. So yeah, picking up the baton here and thinking about our climate side of this project, which is just one small component, one small piece. Robin surveyed the study region here, so the whole Eastern Corn Belt region, primarily southern Wisconsin, Michigan, and then Illinois, Indiana, and Ohio, and the basins within that as well. And so we've established our climate evaluation within those boundaries as well. So we actually, to get a basis and kind of evaluate how the models are basically capturing the Eastern Corn Belt, that was kind of our big first question. You know, how well do models capture what's happening? We need to know what's happening across that region. And so we used a product called DayMet, which is just a gridded observation data set at a 1 kilometer by 1 kilometer resolution scale. And then we evaluated within this climate extremes framework, this working group within the World Meteorological Organization has established a set of climate indices that represent climate extremes, from the hottest day of the year, coldest day of the year, threshold temperatures, percentages of days where you fall above and below 10 and 90th percentiles, and then some other variables like frost days, ice days, tropical nights rather, with certain thresholds that you can see in the table here on the right-hand side. Also with extreme precipitation, the amount of precipitation, 1 day, 5 day maxes, and thresholds in terms of how much of that's coming from the heavier precipitation events. And so we looked at not only the modern period of observations, but also evaluated how well the models are capturing that. So we focused on the CMIP5 models, which were part of, or part of kind of the last iteration of the National Climate Assessment work and the IPCC work, specifically looking at the LOCA method. So what that means is that there are a lot of different ways of downscaling models. And this particular method was a way of capturing a little bit more of the extremes in some of the methods that they use to produce this data set. and it's at a 4-kilometer model resolution as well. And so we basically wanted to compare how well the models are doing over the contemporary period, so we can get an idea of the uncertainty that may be associated with future projections as it pertains to agriculture across the region. And so looking at just a few of these variables, and there won't be any big surprises here, really consistent with the past literature, but just looking at the observed trends from 1980 to 2018, for instance, and looking at the warmest temperature of the year, the annual high, and there are certainly some differences across the Eastern Corn Belt region. So if you're upstream of the Great Lakes, for instance, we've actually seen a cooling in those daytime summer highs. The maximum, I should say more specifically, the absolute maximum temperature that we reach in the summer, there's been suggestions that areas upwind, upstream of the Great Lakes have actually decreased in that maximum temperature during the summertime over this 1980 to 2018 period, while areas closer to the Great Lakes have actually seen increases in this number. And so thinking about the impact of warmer lakes, for instance. Now, reduced heat in the summertime could be a good thing, less stress on corn, soybean, things like that. But what about specialty crops and the impacts around the Great Lakes? Of course, this is where these decisions about what we do and how we adapt to these changes come into play. Looking at another coldest annual low, for instance, we know our nighttime lows have increased across the board, but just looking at some of these specific basins where our observations show upwards of 3.5 degrees Fahrenheit increase per decade over the last 39 years, right? So these are very strong warming trends. And of course, that's going to have impact on an agricultural perspective from overwintering concerns, pest and disease pressure, changing hardiness zones and shifts in crops, etc. And just a couple more real briefly, thinking about the warmest nights above that 90th percentile. Again, pretty clear across much of the Eastern Corn Belt region what we're seeing in terms of warmer summer nighttime temperatures, thinking about pushing crop use, crop energy, and pushing those phenological states much faster, right, through the agricultural production cycle. And then the frost days, increasing the amount of frost days, frost-free days as a percentage, kind of across the board. So when it comes to temperature, there are very similar patterns, right, across the entire Eastern Corn Belt region, or much of it. We know our frost seasons, our last spring freeze, are occurring earlier, and later first fall freezes, and particularly here in Ohio, we've seen even later first fall freezes compared to those early spring freezes in April, for instance. Then turning attention to what we've observed in terms of precip, much of the Ohio, Indiana, Southern Illinois region, Northern Kentucky has seen a big increase in the amount of precipitation over the last 4 decades. Doing some spot analysis, looking at individual stations, for instance, I've plotted Louisville, Kentucky here, where we're talking increases on the order of about 3 inches per decade over the last 4 decades in terms of total precipitation. And so that's a big concern, right? When we deal with persistently wet soils, the increased potential for runoff and erosion, all of the associated problems throughout the region that we're familiar with. Looking at the number of wet days, there's some inconsistency here and some uncertainty across the region, whether we'll see more rainy days or less frequent rainy days with the increasing precip, but certainly in a large portion of Indiana, Ohio, much of Michigan, we see these pretty strong, robust trends in terms of the increasing amount of wet days. And then just the 1-day and 5-day maximum. It seems like Indiana seems to be the epicenter here across the Eastern Corn Belt region from our observation. Intense rainfall, more precipitation, and increases alike. Now, this is looking at it more on an annual scale. We've got additional analyses now looking more at the seasonal scale of things. We know, for instance, that our spring and our falls have really been increasing in the amount of rainfall, but not necessarily the summer, for instance, where particularly here in Ohio, we've seen decreases in our July precip across much of the west, central, and northern portions of the state. So you can intensify basically that hydrologic cycle and getting more rainfall, more intense rainfall, but also short, intense drought periods as well. So very complex and convoluted. Not to really belabor the statistical analysis, but we took this approach, which is called the modified Klein-Gupta efficiency approach, to just look at how well the models are able to capture what's happening across the Eastern Corn Belt region based on what I've already showed you. Now, this is what I refer to as the underbelly of climate models. As a modeler, it's not surprising. We know, we always say that all models are wrong, some are useful. It's very interesting to look at some of the performance of these models across the Eastern Corn Belt region for different variables. And so that's what the graphs here at the bottom are showing you. We don't have to get really deep into the woods, but we're looking for a score as close to 1 as possible on the KGE score. And the different colors will indicate the different scores. We've got different variables along for each of the columns. The 5 different regions and the Eastern Corn Belt denoted by the 1 through 5 and the E at the bottom, and then every model within the suite of 32 models and the ensemble mean. So how well do the models compare to that mean that we often use as well? So single model performance, we know, varies across all basins and across the Eastern Corn Belt region. So different variables perform better than others for certain models. We know that there's some collective model performance that does well. For instance, TN10P, you see a lot of similar scores here across all the models and all the basins. But it does, bring up the question: are there model standouts? Can we come up with a way of looking at a better model ensemble? And so we tried to use what's called a comprehensive rank for an Eastern Corn Belt region, using the verification of this region to come up with a way of ranking and compositing just the best models for our particular region. One of the first things we did was looking at the different ensembles and how you put them together. And basically, if you combine 2 to 3 ensemble members, you get the highest scores. After that, adding models doesn't necessarily improve your overall idea of what's taking place across the region and the performance compared to observations. In fact, the scores actually decrease as we get higher in number in terms of the amount of models that we use for an ensemble. So after all this was put through the wash and the hand waving that I'll spare you today in terms of looking at these ranks and putting all the ranks together, we can come up with a set of the best models for looking at temperature across the Eastern Corn Belt region and a set of best models across the region for precip as well. And then kind of focus on those and their model mean to look at model means, ensemble mean, to look at future changes under these different scenarios of the future. So then we're able to look at the changes and look at consistencies and inconsistencies among the different members. When we look at temperature, generally we've got strong and significant changes that we know relative to our baseline numbers. But there's still considerable spread among the various models, and we can see that in the colors here. So if we just took the first column, this is just looking out mid-century for the 3 different models here, the top 3, and then that ensemble model at the bottom. And you can see there's still a bit of spread among the models. So despite the best models used, in this analysis based on performance, there's still significant differences among the different basin projections, the projections within the basins as well. A little bit more consistency among what we're expecting in terms of extremely wet days, for instance. Model agree that heavier events are more likely under future scenarios, but there's a lot of details you can tease out at the seasonal scale and at the individual model scale when we get down to it. So unfortunately, this isn't a great, I think, format to really highlight some of these changes. But we can look at, for instance, taking the climatology of the lower Maumee in Northwest Ohio and looking at the mid-century range depending on our scenarios. And the 2 scenarios we chose here were basically 4.5, which is some carbon restrictions and kind of limiting it to about 450 by the end of the century. 8.5 scenario is more like what we've called in the future business as usual, but it's not quite business as usual. We're talking 900 to 1100 parts per million of CO2 in the atmosphere. So we can get these ranges of changes within the different basins, which are pretty interesting. And since I'm kind of coming up against my time, I just want to focus a little bit on, some of the precip changes. From the observations, there are pretty significant differences among these basins within the Eastern Corn Belt region. Now we see, around 1,000 millimeters here across the basin, but much more in the Sugar Basin and the McAlpin, the southern reaches, than we do those northern reaches. And so when we look at the amount of change projected in the future for some of these basins, it could be upwards of 70, even 8% increase in total rainfall. Looking at the percentage of change in those heavier events, we're basically bending all of the rainfall in these bigger events, which means that it opens the opportunity also for short-term water shortages during more intense periods in the middle of the growing season. So these are some of the details that we've teased out. And of course, this forms a basis and a foundation for the other components of this modeling team and teamwork, looking at ecosystem modeling and the economic modeling, bringing in the farmer decision making that and the risk and decision making that Robin's going to talk a little bit more about. So kind of in summary, we know sort of what we know pretty well what our recent trends are, but we're trying to develop optimal model ensembles for this region, because ultimately, effective adaptation and mitigation really depends on how we react, I think, to the changes that are happening at these regional scales. And regional can mean different. Eastern Corn Belt or the individual water basin, a lot of the trying to get information and climate information and how it differs between these smaller scale basins is a really important task. So I think a great question is, giving different scenarios of the future, does a 2 degrees C warming versus a 5 degrees C warming really impact our decisions and outcomes greatly? I would argue that it does. But that's what we want to explore a little bit. So what scale is really fine enough to adequately drive decision making? And I think that's all plays into one of our, kind of the objectives we're hoping to get out of the overall project. So with that, I'll turn it back over to Robin. Thank you.
Great, thanks. Well, let me know if you're not seeing my slide here in a few minutes. It should say objective 3, but I think, oh, yep, I'm now the presenter. Great. So building on that climate modeling piece, our next objective was then to identify farmer adaptations. So models, just statistically, how farmer land use and management adaptations to climate, to model their adaptations to climate variability and to any of these broader human system changes.
Robin, we need to share it.
Oh, I need to reshare it? Okay, hold on 1 minute. All right, are we seeing it now?
Yes, perfect.
Okay, great. Sorry about that. So our approach was to specify the relevant set of farmer adaptations under future scenarios using a combination of qualitative, historical, and experimental data. And then the outcome is a model of the likely adaptations of diverse farmers to climate uncertainty under varying market policy and technological conditions. So there are pieces of this that are still being developed, but what I'll share with you today is some initial analysis of the feedback we got from farmers through a survey that we did that had a choice experiment built into it. And I'll walk through what that experiment looked like. So how we did the survey is we purchased a sample from Farm Market ID, which is a kind of standard way to collect a random selection of farm operations across a certain geographic area. We focused on corn and soybean farmers. We actually did stratify by farm size, and that was in an attempt to capture more responses from farms on the larger size, because if we just randomly sampled across the Eastern Corn Belt, we would have had a lot of small farms and very few bigger farms. So we wanted to try to correct for that a bit. And then I pointed out on that map before, we actually did this within those 5 representative watersheds across the Eastern Corn Belt. We administered the survey by mail using the Dillman method, and this happened from about August to October of 2019. We ended up with a response rate of about 27%. And on average, our respondents were 64 years old, farming just under 1,000 acres, 3rd generation farmers, and 64% of them indicated that they had a plan to pass their farm on to a family member, just to give you a little bit of a sense of what this sample was like relative to the population. And so I mentioned we had an experiment embedded in here. So essentially, we presented farmers in the survey with several different scenarios. So here's an example of one. We would say, read this following scenario and indicate what changes, if any, you would make to your operation. And then we had a few pieces that would vary in the different scenarios. So in this one that you're seeing here, we varied the payments per acre if you were to enroll any of your land into a standard retirement program. We also had a variable where the conditions that we described below were going to be more or less common over the next 10 years. So here you can see 8 out of the next 10 years. And then here in this little table, you'll see the other variables that that we essentially manipulated in the experiment. So changes in the planting date. This, for example, is the baseline planting date. These were also standardized to those particular watersheds and built on the work that Aaron already presented. Average rainfall during the growing season, again, this would have been the baseline for this particular location. And then the harvesting date, if it wasn't the baseline, it was 30 days earlier, perhaps 30 days later. We'll see on the next slide. And so in this case, someone was presented with some baseline conditions for planting and rainfall, but a deviation from baseline for harvesting. So then we'd say, under these conditions, what changes would you make? They could select anything, but they could also say, I wouldn't change anything, right? There's nothing about this scenario that would encourage me to change the way that I'm managing my land. When you think about like the use of no-till, that I would take land out of production and perhaps put it into conservation programs. And then we even had this question in here about crop insurance coverage. So we tried to put a few different strategies that might be considered adaptation strategies to these sorts of challenges. And so here you can see the full range of variability in those scenarios. So some people would end up with the kind of baseline conditions, but for planting, based on Aaron's work, we varied those conditions to the planting date being 30 days earlier or 45 days later. With harvesting, it was 30 days earlier or 50 days later. With growing season rainfall, it was 15 inches less, baseline or no change, or 10 inches more. And then conservation payments, there was a baseline and then 100 more or 100 less. And then the probability of those conditions being in place over the next 10 years was basically a 50-50 chance versus 8 out of 10. So farmers would get unique combinations of these, and then we could then look through statistical models at how their choices varied and what they were sensitive to. And so I'm just going to highlight a few of the results in just kind of a visual graphical form. We've been putting together an infographic summarizing some of these results, and so you get to be the lucky group to see these, I think, for the first time. And so one of the things that we saw from our analysis of this data is that there were really kind of two decisions that were being made by farmers, and what explained the result of these decisions is very different. And so we saw that farmers were both thinking about, should I adapt or not? So period, is there something going on that's going to require changes on my farm? And then part two would be, if I've decided to adapt, how should I adapt? And what we saw through our data is that the decision about whether or not to adapt was really driven by farm and farmer characteristics. So for instance, bigger farms were more likely to just adapt, period. That would be a farm characteristic that we examined. Farmers who were perhaps more conservation minded, since some of these were kind of traditional conservation practices, perhaps they were more likely to adapt. But then when we looked at how they adapted, so again, examining whether, the discrete probability of adapting, yes or no, versus the probability of perhaps changing your tillage practices or installing more drainage tile, we saw something very different. And there we saw that it was really their personal experience with the impact of climate change that drove those specific choices. So we had certain types of farms and certain types of farmers who were likely to adapt at all. And then within that group, what we saw is how they adapted depended on what they were struggling with the most. So you can think about, too much rain in the spring might then lead you to want to install more drainage tile as a way of kind of getting that water off the landscape. So that was one kind of initial set of findings from this work. And then when we start looking specifically at those adaptations, this is what we see, is we really saw kind of three categories, I guess, of farmers or adapter types, as we're calling them here. Here at the bottom of the screen, you see the never adapters. So about 28% of our sample, under no circumstances, changed anything on their farm. So no matter what scenario they were presented with, no matter what combination of those variables that I talked about a third of our farmers were like, I'm not changing anything. I'm not changing anything. And what we saw is that that group had less experience with the impacts of climate change. So they were much less likely to report having these kind of experience these negative impacts. They also employed more traditional farming methods. For instance, they had a greater probability of using conventional tillage. We also saw that they had more farming experience and were older, which kind of goes hand in hand. And we saw that they, on average, were operating smaller farms. So this gives you a little bit of a sense of the type of farmer who perhaps will be resistant to making changes. One, they may not feel there's a need to based on their experience, but they might have been doing this longer, might be less excited about making changes moving forward. and might be operating at a scale that makes it harder to make some of these changes as well. And then over here, you can see about half of our respondents we're calling the sometimes adapters. These were folks who were more likely to have crop insurance than others. They were often more concerned about climate change broadly, apart from those specific impacts. And then they had some overlapping characteristics with this third group. They had more experience with those negative impacts of climate change, and they tended to operate larger farms. And then we had a minority, about 23%, that we're calling our multiple adapters. These are folks who adapted more than once, so to multiple scenarios, putting multiple adaptations in place. So these are maybe your most kind of forward thinking when it comes to dealing with these changes. And again, they had more experience with those impacts of climate change. They operated larger farms, so that was something all the adapters had in common. But this group was a little bit different. They also were more likely to plan on keeping the farm and the family moving forward, and they were more educated. So we start to see that the farmer types are diverse, right? They're making different decisions, and the reason they're making those decisions is varying as well. And then just to highlight, because I know this will be of interest, we asked them, you saw the examples of what we allowed them to kind of select in response to the experimental piece. We also had another section of the survey where we looked at an even more comprehensive list of adaptations. And generally, we saw these as 4 of the most preferred adaptation strategies. So at the bottom, we've highlighted 2 of the ones that we would call kind of a short-term focus. So something farmers might do to get kind of an immediate benefit. So installing more drainage tile was a very popular strategy, which again, might make a lot of sense for your production goals with spring planting, but may not be a great thing for some of these other societal benefits. And then we also saw changing their insurance coverage as a very common adaptation strategy, which again, I think is focused on this kind of near-term risk management. And then we did see 2 other pretty popular strategies that I would argue again are maybe focused more on long-term benefits, more of a sustainability focused approach, perhaps has benefits both to the farm but also to society at large. And this would be retiring land in conservation programs and also increasing the use of conservation tillage. So we see a pretty even mix, I would say, of kind of maybe emergency management strategies versus more long-term thinking about resilience in the system. So our next steps, and I'll try to wrap up here in the next 5 minutes or so we have plenty of time for questions, is to then think about, okay, in the face of these climate risks and uncertainties that influence farmer adaptations, and we're seeing that, you know, a good majority of our farmers are thinking about how they would adapt their operation in order to deal with some of these impacts they're experiencing, then what set of policies and programs will balance agricultural production with critical ecosystem services and ultimately achieve a more sustainable and resilient agroecosystem? And to answer that question, we have to do a little bit more than what you've heard about so far. So far, we've just kind of talked about our regional climate change model, how we're looking at how farmers might be adapting to that based on different climate scenarios. The next step then is to develop our regional economic model. So I mentioned we have a team of economists working on this project as well. And their goal is to develop a model that accounts for price feedbacks in simulating land use and management adaptations. In order to do this, they're developing a model without explicit uncertainty and simulating it for a baseline climate scenario, and then parameterizing it to account for uncertainty and some of this heterogeneous or diverse farmer behavior that I just talked about. And then ultimately the goal here, the outcome, is a fully specified model of the Eastern Corn Belt economy that accounts for spatial heterogeneity and uncertainty and generates predictions in the allocation of land to different uses and management under future climate scenarios. So again, looking at these bigger economic drivers, but also some of these behavioral pieces I talked about, and looking at, as we look into the future, how might we expect land use to vary? Will we see more land go into conservation retirement and out of production? And for that land in production, would we see perhaps changes in the way that land is being managed? And so that's this kind of piece over here. We have their regional economic model that both is kind of feeding into farmer adaptations through those kind of retirement payments, but farmer adaptations also feed back into that regional economic model to think about what's the landscape going to look like in the future. And we can run different, price scenarios within that model and think about how might these things, again, influence how those decisions will change over time. The next step then is to model the changes in that broader suite of ecosystem services. So determine the extent to which climate variability and changes in farmer land use and management will impact ecosystem services. And the approach here is to quantify these impacts using spatially explicit models of farmer land use management decisions, and then these process-based agroecosystem models that can tell us something about the potential yield under different conditions, not only climate conditions, but also other sorts of management decisions that might be made on the farm. Can look at impacts on water quality, can look at carbon sequestration, can look at even climate regulation at a micro level. And the outcome here is an improved understanding of the realistic impacts of climate change on, again, we've selected these 4 services, but crop production, carbon sequestration, water quality, and biophysical, again, kind of micro level climate regulation. And so you can see this here, where again, the decisions that farmers are making that we've assessed through our statistical model of farmer decision-making feed into this set of ecosystem models that will tell us something about how that landscape changes in response to those farmer decisions. Oops, I think that, oh yeah, so I forgot. So Kai Zhao is the lead on this piece, and he's an ecosystem modeler at Ohio State in the School of Environment and Natural Resources with me. And he shared one slide with a few highlights from what he's been finding so far. What he's seen so far in his early work is that climatic effects on crop yields vary from one location to another, showing that strong local heterogeneity, so consistent with what Aaron pointed out, there is this heterogeneity across the Corn Belt. And when we look at that carefully, we do see some significant differences in yield from one location to the next. So crop responses to climate change are not unidirectional, but nonlinear, and determined interactively by both temperature and precipitation. So that's something that's come out of their initial work in kind of setting up these models. They also see that local predictions provide more reliable, actionable information. So a generic regional model had 500% error relative to local models when tested in Ohio specifically, just as an example. And then also climate-induced land use activities will feed back to regulate climate by affecting the carbon balance and altering surface biophysics. So the biophysical effects on local climate are much stronger than the overall carbon dioxide effect. So those are just a few highlights that Kai wanted us to share with you today. And then ultimately, as we bring all these pieces together, I mentioned our goal at the end is to identify these optimal policies. So find the socially optimal agricultural, energy, conservation, any of those categories are fair game, but policies and programs that we think will provide the best balance across this set of services. So the approach is to create a principal agent model. So think of a kind of, an all-knowing government actor in which that actor decides on an ensemble of policies, while farmers and firms choose their optimal decisions. So to transition into different land use, to plant different crops, to make different investments. And so the outcome here will be a novel framework that embeds the behavioral heterogeneity that I talked about with the land and labor markets, which are in the big regional economic model, and projected changes in the agroecological outcomes, which is the ecosystem services piece, into this integrated model that determines what the optimal policy ensemble would be for a given future climate scenario under different conditions of uncertainty. And so you can see that all depicted here with lots of lines and arrows flying around, but essentially our kind of end piece is to do this policy analysis where those policies feed in and influence farmer decisions, which feed through this regional economic model. And ultimately all of this comes together to help us assess what are those sorts of things that we can do to intervene to ensure the sustainability and resilience of this system moving forward. And then finally, like all good researchers, we have an objective around engagement, making sure that the farmers we're working with other stakeholders, have access to our science, that we translate that science in ways that will be useful. And so a goal here is making the climate variability and the adaptation strategies relevant for a diverse set of stakeholders. And so we have a set of in-person and online products that we are developing for each of these 4 key outputs. So you've heard a little bit about the climate trajectories and the farmer profiles today. And then as we start to quantify the agroecosystem impacts and the optimal policies, we'll be developing again, a set of products, videos, infographics, short write-ups, and kind of sharing that broadly. So the goal here, the outcome is enhance stakeholder capacity to conduct climate science programming, to better engage farm clientele, and to even lobby for more informed policymaking, given this better understanding of what the future could bring. And so if you're interested in learning more about the project, you can go to our website. It's listed here, u.osu.edu /Agroecosystem Resilience. We've got a set of videos that we've developed that kind of overview the project, talk more about the climate piece and the adaptation piece that you heard about today. I also have given some longer talks on the adaptation piece, and you can see an example of one of those here if you want to hear more about that. We also have a series of infographics we've developed. So here's the one that summarizes some of the key takeaways from the work that Aaron discussed about what we might expect in terms of potential shifts in temperatures and precipitation. And then you saw little bits of our farmer infographic. It's kind of in draft. We have an advisory meeting coming up in a month or so, and we want to get their feedback on it before we release it. But again, just trying to summarize some of what we're learning in a user-friendly way that perhaps will be of use and of interest to broad groups of individuals working in this space. So at that, I will stop and see if we have any questions. I just wanted to thank NIFA, where the funding came from for this, the broader project team. I've listed some of our principal investigators, but lots of graduate students, all of our stakeholder advisory team. And of course, you can always reach out to Aaron and I with more questions, or we can connect you with other members of the team as well.
Okay, we have had one question so far, and oh, we've got more rolling in, but the one that was asked during your presentation, you had discussed the characteristics of farmers and whether they would be adopters. And the question comes up a lot. What about rented land versus ownership of land? Was there any analysis of that?
Okay, so I think we might be referencing this slide. So we did look at rented versus owned land. We did not see an effect of that in this particular analysis, but that could be for a couple of reasons, because we do often see that in kind of the broader study of conservation decisions in agriculture, which again, some of these adaptation decisions could be classified kind of classic best management practices for conservation, you know, cover crops and no-till and whatnot. Others of these are not, right? Like changing your insurance. We even had options in the broader survey about selling your farm, renting out your land, just as a strategy for dealing with the economic pressures. But we do know from those conservation specific sort of adaptations that we do see differences where some of those are less likely on rented land, which is why there's been a big push to you know, engage especially non-operating landowners more often in these conversations. We don't see that effect here. It could be partially because some of these are much broader than the sets of practices that you would typically see that effect, but also because the only way we could capture it for these particular decisions was through what proportion of their farm was owned versus rented. This wasn't specific to a field, right? So we weren't saying like, pick a specific field, think about these conditions in the future and what would you do on that field, and is that field owned or rented, right? That would almost have been another level in the experiment where we could have randomly assigned people to like answer these questions for a rented field, answer these questions for an owned field. Then perhaps we would have been able to tease out that signal a little bit more. But just looking at the kind of proportion of rented versus owned acreage on the operation, we didn't see an effect of that.
Okay, thank you. Cynthia asks, or did you have anything to add, Aaron?
Not to that one, no.
Okay. Cynthia asks if any of the panelists are asking about water catchment as far as cisterns, holding ponds, etc., being looked at by farmers as a drought mitigative or adaptive approach.
That's a great question. And Aaron, I'm going to ask you, like, you should know my survey better than I should, but didn't we ask that in the longer list of questions, but it wasn't a very popular response?
Right, yeah.
Yeah, so we have a full report of the survey results available on that website, the u.osu.edu website. And so you can see the responses to every single question in the survey. So we have a lot of other results outside of the experimental piece that I shared today. And in our laundry list of potential adaptations, we did actually look at that piece of kind of capturing drainage water and holding it for the dry periods in the summer. That was not a very popular approach. So my behavioral response to that was that that's not the impact people are worried about right now, but they're not experiencing to a strong enough degree those dry periods for that to be a big enough a concern to invest in the amount of space it would take, right, in the cost of constructing those sort of retention ponds. It seems that they're really concerned about the rain in the spring, which makes sense given some of what we've seen in the last several years.
And if I could add there too, I mean, from an outreach standpoint, when you talk to folks, I mean, it certainly comes up at almost every meeting that I attend and present, because should it be on our radar for future adaptation measures? Absolutely. I mean, from a climate perspective, I think it should. But again, it varies across scales, so it's going to matter really locally whether or not that's something that you can, one, afford to do, or whether, two, it's worth the time to do. But it does cross scales between the rural and the urban gradient as well, because, you know, municipalities and rural communities can be thinking about that as well. When we think about managing, you know, individual farms as part of larger landscapes of the whole county, for instance, and soil and water conservation districts are thinking about that. So I think it is on the radar, but it wasn't something, as Robin said, that we saw a big response in terms of our survey.
We also did look at the positive impacts of climate. So this presentation has been on the negative side of things. Too much rain, too hot, get rid of the water. But we did also look at kind of, you know, opportunities presented by climate change, like double cropping, and we didn't see a very strong response to that either. The response from farmers was definitely more on the negative end, the challenges, and adapting to deal with those challenges versus adapting to take advantage of opportunities.
Okay, I did want to mention that there's a poll open right now, and if you wouldn't mind completing that in the next minute and a half or so, that would be much appreciated. Kathleen asks, we see here larger farms and smaller farms on the adapter types. How big was the smallest farm in the survey?
Ooh, that's a good question. This question, I get a question a lot about larger versus smaller, and what is that? And it's like, well, it's all relative, right? This is a probabilistic statistical model, so it's all relative. But we typically, when we're building our sample, we exclude farms under 50 acres. Plus these are they have to be farming corn and soybeans. So I would have to look back and see, but remember we also stratified by farm size categories, so we could get equal amounts of farms in a kind of, you know, couple 100-acre range to the 500 plus to the 1,000 plus to the 2,000 plus. So when I say smaller farms here, not a 100-acre farm, probably more like a 500-acre farm, you know, when you look at the spectrum. But again, you can see, I think the distribution of farm size should be in that report, but if someone's interested, feel free to email me as well. But we purposely built our sample to be biased towards bigger farms. So yeah, relatively speaking, we're not talking like hobby farms or just livestock operations with minimal planted acreage. These are pretty big farms on that scale.
Okay, thank you. We've got 2 questions in the queue yet, so do submit your question if you have it. Cynthia asks, with a desertification line advancing across the U.S., would you expect a change in more precipitation to less, or would there be more likelihood of land stress with increased erosion and less water retainment?
Yeah, Cynthia, I can answer that one. Yes, all of it, right? So, you know, one of the things that we see certainly from the projections here in the Eastern Corn Belt region, we do expect that largely what we've seen in fall, winter, and spring is a continuation of the trends. Wetter season during the off season, especially in spring and winter as we move into the future. It doesn't necessarily mean that it's everywhere all the time either. Of course, when you go out in more western areas, western Kansas, Nebraska, as you mentioned, kind of that movement of the 100th meridian is in play. But we see seasonal shifts, for instance, seasonal jet stream shifts to where while we're getting more rainfall in the off season, during that summer season, projections show an increase in drought potential, an increase in drier, you know, shortages of water during the growing season. And so it's kind of a mix of both. And I think, you know, I tried as often as possible to put it in context of kind of this changing hydrologic reality. We're intensifying the whole cycle, not just the precip that falls, but also the evaporation, right? We increase warmer temperatures, we get more evaporation, a larger percentage of the time. We get that evaporation up, we condense into clouds, we form more precip. But with evaporation rates increasing a bit as well, that can drive us very quickly into, those situations. And so while I think a lot of the attention lately is because of these 20, for instance, in Ohio, 2017, 2018, 2019 are all in our top 10 wettest years on record going back to 1895. So everyone's thinking water, 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 water. And it's true. I mean, we have to deal with that, especially in our spring and fall, but we're also seeing these summer shortages and shortage of rainfall there as well. So it's really both sides of that hydrologic reality are in play.
Oh, I think you're muted, Hans. See your mouth moving, but.
Sorry. Yeah, I was. That's so elementary. Really disappointed in myself. Jason is asking, is there awareness among the landowners you're working with about the percentage of carbon in their soil and whether or not it's increasing or decreasing?
Ooh. You have an answer to that, Aaron?
Generally, yeah. I mean, anecdotally, yes. I mean, people are thinking about organic material. They're thinking about carbon storage, adoption. I mean, we can go onto the side of cover crops and no-till and things like that. I mean, I think there's an awareness. I don't know that we've tested like a percentage of those that are adopting those certain aspects. I mean, I'm involved in other projects where we know the literature is wide as the ocean on the potential benefits of cover crops and diversification and interseeding and all these things that we know help improve carbon in the soil, but adoption is still really slow. And so trying to understand the mechanisms and the levers of why that is, from markets to insurance to all other things are on the table here. But largely speaking, while it's part of the awareness, and I think it has to be, it's a very important part to think from a climate adaptation standpoint, to what degree we're actually adopting those practices, it's still pretty slow.
Yeah, I would probably say the same thing. We haven't empirically looked at that in any of our survey research. Maybe danced around the idea of soil health a little bit, but not looking specifically at carbon. But yeah, anecdotally, I work with soil scientists a lot on other projects, and I would say that on one hand, the comment you'll hear from folks in that space is like soil health is making a comeback, where farmers are more aware of and recognize the importance of. But yeah, we're not where we need to be, that we don't have that kind of nuance in our soil testing, that farmers are not as aware as they could be probably of some of what's going on.
Okay. Cynthia's got another question, and this is kind of an interesting thought. In your opinion, are weather patterns changing to a more monsoonal type of weather pattern as far as a rainy season versus a dry season?
If you just strictly go rainy season, dry season, and you base it on the projections that we see rainier fall, winter, and spring, and dry summer. I mean, I can see where the connection could be made to, is this more like a monsoonal type flow? Now, monsoons is a specific, type of weather pattern often associated with changing circulation that brings in tropical moisture over certain areas over certain periods of time. We think about the Indian monsoons, the Chinese monsoons, the U.S. monsoons in the Southwest U.S. I don't know that I would fully call it that, because again, even though we get individual areas throughout the spring, for instance, that are decreasing rainfall for some months, overall summer, we're still seeing increases in rainfall throughout the region. And again, so to say we've switched or going to a monsoon, I think it's an interesting question, thought experiment, but it would be an opinion for me to say. I think I don't tend to think of it that way, but it's not a stretch to think about it if you're just basing it on a rainy and dry season, for instance.
Okay.
Yeah.
We've got one more question, and then I believe we'll wrap up as we approach the top of the hour. Kathleen asks, what adaptation would you recommend for sustaining plant yields in this changing climate?
Do we both get to answer that?
Maybe
Yes.
we should.
Okay, I'm going to preface the fact that neither Aaron nor I should be answering this question based on our expertise. I'm a behavioral scientist, so I'll put on my pretend to be someone who knows something about that hat because I work with folks like that. But I do feel like I still hear a lot of push for cover crops and no-till in combination as a resilient strategy for dealing with the fluctuations, the hydrological extremes. The idea there is around soil health and better filtration when you're getting all the water, better soil moisture capacity when you're not getting as much water. So I think from a resilient standpoint, I still hear a lot of support for thinking about soil health more broadly, and that combination of practices being one that could be really critical. But I think it's tricky to answer that question because there are just so many different kind of issues people might be struggling with, but that's one that I think is probably broadly promoted.
Yeah, and I would say, you asked what adaptation. I think it's a tool belt. It's a tool belt that's full of regionally specific or watershed specific adaptation strategies that work for your farm, your family situation, your soils, your slope. All of those things are really, really important at the local level. And so, there are folks that have tried, for instance, no-till or cover crops, and they don't seem to get them to work. And there are various reasons why that doesn't work. But ultimately, I think the adaptation strategies that are tailored as specific to your local region as possible also then help combat the climate impacts that you're feeling in your particular area as well. And so from a standpoint where climate and agriculture are coming together, we're at that door right now. We're tapping on that door and saying, okay, what strategies really do work and where do they work? And farmers, I know, want that information. Agriculture wants that information. And so that's where I think that the next 5 to 10 years will really take us in terms of this, climate impacts on agriculture throughout the region.
Yeah. And I think, one of the end goals of this project is to be able to answer that question, to be able to say, here's the set of things that if we can encourage these types of decisions, we're going to see a kind of a net win at the end of the day. So there's a lot of interest in increasing tile drainage. Well, that solves the big spring rain problem, but that could exacerbate downstream issues. And so if we're going to do more drainage tile, it'd be nice then to use those holding ponds so that water isn't just being flushed downstream every spring. So I think, yeah, we're hoping to get a better answer to that question as we pull these pieces together.
That's the perfect ending.
Dun, 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 dun.
Yeah. So Cynthia did have one question, just as we wrap up. If the participants want to email you, can you make the slide deck available to them?
Sure. In fact, we'll post it on our website as well. So that's not a problem at all.
Okay, excellent. Well, thank you everybody for sticking around for the entire hour, and thank you to our presenters, Aaron Wilson, Robin Wilson. It was a very engaging presentation. Be glad to have you back anytime.
Well, we'll circle back when the project's over with part 2.
Excellent.
All right. Thanks, everyone.
Have a good afternoon.
Thank you.
Bye.
Thanks, Hans. Thanks, Robin.
Yeah, thanks.